to introduce our speaker for today's colloquium, Dan Spielman from Yale, who I had met more than 20 years ago. Dan grew up in Philadelphia, and in the fall, I believe, of 1987, and maybe spring of '88,
yes.
I had the pleasure of having Dan in my Math 370 and 371 class. And it certainly made the...
As a high school student.
When he was in high school, growing up in Philadelphia. That's right. And it certainly made the class livelier. Well, it turns out he's been, well, he's been certainly busy in the time between then and now, and has various things to show for it. In particular, in 2008, he won the Gödel Prize, and in 2009, the Fulkerson Prize, and in 2010, this year, at the ICM in Hyderabad, he won the Nevin Linna Prize for his work. And his title today, as you see, is on Spectral Sparsification of Graphs and Approximation of Matrices.
Okay, thank you very much. So one comment which I've mentioned to many of you here, I haven't been back in this building for about 20 years. And the only thing I'm sorry to say is that it hasn't been redecorated since then. But I guess it is nice to see that it looks the same.
Is this room entirely different?
No, this room I never saw. Yes, that I will do. This room I never saw. Anyway, so I'm going to talk about work from a couple of papers. The first of them written with S-Tengl, who's at the University of Southern California. A few of them written with Nikhil Srivastava, who was my PhD student and is now a postdoc at IIS in Princeton. And one of them written with Joshua Batson, who was an undergraduate at Yale when he worked with me and is now in graduate school at MIT. So let me give you an outline of good. Consider what we're going to do. I'm going to begin by describing for you a notion of what it means for one graph to approximate another. There are a couple different reasonable definitions, but I will give one that's motivated by concerns from numerical linear algebra foremost, though I won't need that framework to describe it. Once we have a notion of what it means for one graph to approximate another, we can ask ourselves the question of whether or not a graph can be approximated by a sparse graph, where by a sparse graph I mean one having few edges. This is the problem we call sparsification. And we will take a look at how well arbitrary graphs can be approximated by sparse graphs. And as I said, the definition or our notion of approximation will be induced by quadratic forms that are related to the graphs. So really we're going to turn this into a problem in linear algebra. And we're going to talk about the question of, if I have a quadratic form represented as a sum of rank 1 matrices, or outer products, can I approximate it well by a sum of a small number of those? We'll see how well we can do that. And then I will finish, assuming there's time, by relating this to some other problems. Some work by Bourgain and Safiri called the restricted invertibility theorem. The Cadison-Singer conjecture seems related to this, and probably some other problems related to approximating the asymmetric traveling salesman. So there's a lot of relations that will pop up. I'm going to try to do everything at a high level and say everything at least 2 or 3 different ways. So if you have questions, don't be afraid to ask. So first, I'm going to try to assume that everyone knows what a graph is. But for me, it'll always be a triple. I will usually talk about the vertex set V, the edge set E. And I'll often deal with weighted graphs, where for me, the weights will be given by a function W that assigns edges non-negative numbers. I'll have non-negative weights on edges. I'm going to find it very useful when I want to talk about approximation to be able to think of graphs as giving me functions, or in this case, a quadratic form. And the most natural quadratic form for me is, okay, if the quadratic form takes taken as an input, a function from the vertices to the real numbers. Or think as a vector, which gives a value to every single vertex. The value of the quadratic form will be the sum over edges of, okay, if the function is x, you take the difference across each edge of the value of the function and square it, times the weight of the edge. So to any graph, I will associate this quadratic form. And of course, once you write it that way, you know it can be written in the form x transpose Lx, where L is a matrix. In this case, it is the famous Laplacian matrix of the graph. I'll do an example in a minute to help clarify this notion. But this is the way I'm going to think about graphs. It's really an isomorphism between quadratic forms of this form and graphs. For those who are impatient, now let me just quickly tell you our notion of approximation. We will say that one graph approximates another, or is an epsilon approximation of it, if their quadratic forms are epsilon approximations of each other. Meaning, for every vector x, I would say I'll say that h is an epsilon approximation of g, if for every vector x on the vertices, the value of the quadratic form in H is within a multiplicative 1 plus epsilon factor of the value of the quadratic form in G. So it's a very strong notion of approximation that we're looking for. This is going to be our notion of approximation, but first let me be concrete and do some examples. So let's say here's a graph that I've drawn. Let's imagine that all the weights of the edges in the graph are 1. That will make our life a lot easier. And now you have a function on the vertices, which I've drawn here in black. I don't know if you can see it. -3 down at this vertex, down to 3 at this vertex. If you now want to figure out what is the value of the quadratic form, you take a look at every edge. You take a look at the difference of the value of this function across the edge. For example, this edge, the difference is 3. You square it. And then you sum those squares, and that gets you the value of the quadratic form. Okay, so this hopefully will help clarify the notion of a quadratic form that we associate with the graph. Here's another very important example, which is when our function only has values 0 and 1. For example, I have 0 on these two vertices and 1 here. Then, in the quadratic form, you're only going to see terms that go from a node with value 0 to a node of value 1. And in this case, you'll just pick up the edge in the middle in the quadratic form, and the value will be 1. So this is an important example, because this is what happens when x is the characteristic vector of a set of vertices. By which I mean you pick some set of vertices, let's call it S, and x is 1 for all the vertices in S and 0 outside. When you do that, this quadratic form is exactly going to capture the weight of the sums of the weights of the edges on the boundary of S. So going from vertices in S to vertices not in S. This is the sort of thing that people in graph theory like to look at a lot. A lot of problems in graph theory relate to what we call cuts, which is really measuring what is the size of the boundary of a set of vertices, where the size of the boundary might be the number of edges leaving it, or the sums of the weights of the edges leaving it. So this is why this is a notion that comes up a lot within graph theory and computer science. Okay, so this is an important example. Let me do a quick review of a few facts about Laplacian matrices of graphs. So first, I define them just by telling you what the quadratic form was. Most people like to define them by telling you what the matrix elements are. And I will give you that definition. It's nice to get it. I don't personally like it because almost everything you want to prove about it, you will prove by thinking about the quadratic form. And it's more obvious there. But if you want to think about it, the Laplacian can be written as the difference of two fundamental matrices associated with a graph. This one DG we call the degree matrix of a graph. That is, it's a diagonal matrix. And the rows and columns are indexed by vertices. So the entry corresponding to a vertex on the diagonal is its degree. That is the sum of the weights of the edges attached to it. So the degree matrix minus the weighted adjacency matrix. So the adjacency matrix of a graph usually is, if it's an unweighted graph, if you have nodes I and j and they share an edge, you put a 1 in the matrix. You have a 0 elsewhere. Well, here we do it with a weighted adjacency matrix. So the off diagonals corresponding to edges, you have the weight of the edge there. Okay, it might not be so important for this, but you can write the Laplacian as the degree matrix minus the adjacency matrix. And then you can quickly see that this is a positive semi-definite matrix. Well, actually, sorry, you should quickly see it from the quadratic form. The quadratic form is never negative, of course. It's harder to see from the matrix representation. Okay, there are other things you can check very easily from the quadratic form. For example, if the graph is connected. That is, if you get from any vertex to any other vertex by a path, then the null space of the form is just the span of the all-ones vector. And if they're different connected components, you'll take the constant vector on each of them and that'll span your null space. We'll always look at connected graphs. And as a matter of fact, I'm going to usually forget that there's a null space. You might see me writing the Laplacian, the inverse of the Laplacian. Don't worry, I mean the pseudo-inverse. So just work orthogonal to the null space and we'll be fine. Because we know what the null space is, it doesn't pose an obstacle. Okay, another important property of the Laplacian is you can write it as a sum of elementary matrices. In this case, you can think of you writing it as the sum of a Laplacian matrix, one for each edge. So I will use L sub uv to denote the Laplacian of edge uv. It's just an elementary matrix which gets you this term x of u minus x of v squared. And for example, for the edge from vertex 1 to vertex 2, this would be the elementary Laplacian matrix. One's on the diagonal minus one's on the off diagonal, and you can write that as an outer product. of an elementary vector that I call corresponding to that edge. It's got a 1 in one position and a -1 in the other. Okay, that's for the example of the edge from vertex 1 to vertex 2. You can do that in general. So we can just write the Laplacian as a sum of, for every edge, of a weight of the edge times an outer product of a vector corresponding to that edge. Where to fix notation, my vector corresponding to an edge from node U to node V is delta U minus delta V, where by delta U, I mean the elementary unit vector in direction U. So 1 in position U, 0 everywhere else. I would use E, but E is always going to be an edge here. So we use delta. Okay, so I can write the Laplacian as a sum of outer products. That's going to be important later. Okay, now we want to define inequalities and approximation. Let me do that a little bit more carefully. We're going to borrow from, well, I've first seen it in operations research, this funny curly less than or equal to. I will say that one graph G is less than or equal to another graph H. And this is for weighted graphs. Well, there are two equivalent definitions. One is that the Laplacian of H minus the Laplacian of G is positive semi-definite. That's equivalent to saying that the quadratic form in G is always less than or equal to the quadratic form in H. So this is what I will mean for one graph to be less than or equal to another. It's really overloading the notation. You should probably define it for the Laplacian matrices themselves, and then I'll say I'll do the same thing for the graphs to make my life easy. Okay, this is what I mean for one graph to be less than or equal to another. Given this, I can almost talk about approximations, but I want to have a little wiggle room. So let's also talk about what it means for one graph to be less than or equal to k times another graph. Well, that's really the obvious definition. I could say it happens if the quadratic form in G is always less than or equal to k times the value of the quadratic form in H, for any k. Or actually, you can just talk about the graph k times H, which you get by multiplying the weight of every edge in the graph H by this number k. And that'll be the same thing. So you can talk about multiplying a graph by a number. It's probably easier to think about multiplying the Laplacian matrix by a number, and it's the same thing. Okay, now I've got a notion of inequalities on graphs. I can make my notion of approximation more precise. For graphs G and H, I will say that H is an epsilon approximation of G if H is less than or equal to 1 plus epsilon times G, and in turn is greater than or equal to 1 over 1 plus epsilon times G. I will warn you that in different papers I use different definitions. But this one is convenient. Usually in talks I put a 1 minus epsilon there instead of a 1 over 1 plus epsilon, but it's easier, but putting the 1 over 1 plus epsilon is nice because then the relation is symmetric. So I made a slightly messier formula so that H is an epsilon approximation of G, if and only if G is an epsilon approximation of H. It's convenient. Okay. Or you can think of this, of course, as the value of the quadratic forms for all vectors x is always less than or equal to 1 plus epsilon and greater than or equal to 1 over 1 plus epsilon in ratio. Yes?
This is clearly some approximation, but
yes.
If we think of, say, topology in metric spaces, we could say that H is less than or equal to some positive constant times G and bigger than or equal to some other positive constant times G. And that's some sort of pseudo-equivalence or something like that.
Yes.
Is that a useful notion? Does that help separate the graphs into some kind of clumps that you can analyze?
Let me think. I don't know that it separates them into nice clumps because there's probably a big continuous structure. But they won't cluster cleanly, unfortunately. From any graph to any other graph, I'll be able to make a sequence of graphs that I'll unfortunately interpolate between them. But this is actually a very useful notion. We'll see some examples in a moment that some graphs are very, very nicely characterized by being good approximations of the complete graph and some others. Right. So yeah, you'll see some good notions that way. So let me give you just actually a couple of implications of this notion of approximation. The first one, it's very easy to show that when you have this sort of approximation, the Laplacians of H and G have very similar eigenvalues. To the extent that their eigenvalues are isolated, you can say they have similar eigenspaces. A nice fact is this relation implies the same relation holds for the pseudo-inverses of their Laplacians. So if the Laplacians approximate each other, so do the pseudo-inverses. That's useful because there are a lot of quantities that you write in terms of the Laplacian or the pseudo-inverse of Laplacian. For example, my favorite metaphor for a graph is when I take every edge and treat it as a resistor. And I can then say, okay, what if I want to measure the effective resistance between two vertices in the graph? That turns out to be a quadratic form in the pseudo-inverse of Laplacian. So when I have this sort of approximation, I know that the effective resistance between pairs of vertices is similar in G as in H. It also tells you things about random walks on the graphs. Our real motivation for doing this work was this tells us that the Laplacian of H is a good preconditioner for the Laplacian of G. This is a concept that comes up in numerical linear algebra. And it tells you that if you want to solve systems of linear equations in G, you can actually, suffices to solve systems of linear equations in H. And you can get as good solutions as you want to the systems in G as possible. Hopefully H is something for which it's easier to solve linear equations in. But that is not the goal of today's talk. That'd be a different talk someday. But that was our real motivation for this. So really this definition is motivated by the numerical, it's stolen from numerical linear algebra, it's fair. They just weren't thinking of it in terms of graphs. But they certainly use it in terms of matrices. Okay, so this gives us then the problem we call spectral sparsification. The question is, you give me an arbitrary graph G, and it'll be its number of vertices. Can I find a sparse graph H that is an epsilon approximation of G? And how sparse should it be? I wrote here O tilde of n. That means I'd like it to be some constant times n. But if you don't get us that at first, we'll be happy with n times log n, or n times log squared n, or I think in Jean-Claude in my first paper on this, it was closer to n times the 33rd power of log n or something. But you got to start somewhere. So this is our sparse approximation problem. We said, given any graph, we want to find a weighted graph that is a good approximation of it and has few edges. I'll show you you can, and there'll be varying degrees or trade-offs between how good an approximation we can get and how quickly we can compute it. I'll mainly tell you about the best approximations today. So I want to give you one of our motivating examples. You know, the first question is, why should this even be possible? Well, we knew a few examples. In particular, we know that expander graphs are good approximations of a complete graph. So the complete graph is the graph with all edges. Say, weight one. Out of curiosity, how many of you have run into expander graphs before? Okay, not many. So I should first tell you that expander graphs are the greatest gift that pure mathematicians have ever given computer scientists. They are everywhere in theoretical computer science, meaning within algorithms, within theory, within pseudorandom number generators. When I was in graduate school, you could not be a theoretical computer scientist and function if you did not know something about expander graphs. You were just not competitive. Okay, but that's not a definition. So let me try to give you one or two definitions. Usually we think of expander graphs as, we usually think about an infinite family of graphs, where the degree, the number of edges attached to each vertex, remains constant as the number of vertices grows. And an intuitive definition is roughly that every set of vertices in an expander graph has a very large boundary. If you take any set of vertices that's less than half of them, a constant fraction of the edges attached to them will be leaving. That's true for all. You can define them other ways. You can define them by saying that random walks mix very quickly on them, as quickly as on any other graph in some sense. So random walks mix quickly. Spectral definitions of them are very nice. I actually divide the spectral bounds into two types, weak expanders and strong expanders. In weak expanders, you just need that as all the eigenvalues of the Laplacian are always bounded away from zero. All the non-zero eigenvalues, that is. There's always one zero eigenvalue. You want all the others to be bounded away from zero by some fixed constant as n grows large. Those are good enough for many applications, but not all of them. I'll also talk about what I call strong expanders, where actually all of the eigenvalues of the Laplacian are concentrated near d, the degree. All the non-zero eigenvalues again, and those exist. So this is a spectral definition of them. You can show that when you have a strong expander, it is a very good approximation of the complete graph. So let me give you a proof of that. So if you take a look at the complete graph, it's an elementary exercise to check that all non-zero eigenvalues of its Laplacian are in fact n. You should really think of the complete graph as being like an identity on this space. So I'll write that here as for all vectors x of norm 1 that are orthogonal to the all 1's vector, the value of the quadratic form in x is just n. Well, we know a similar thing for deregular strong expanders. Because all of their eigenvalues are close to d, it means for all vectors x, the value of the quadratic form is approximately d. This just comes from, I guess, the Courant-Fisher characterization of eigenvalues as optimizing quadratic forms. So this is really a statement that when you have these strong deregular expanders, all the eigenvalues are highly concentrated. This means that if I take this expander and now multiply the weight of every edge by n over d, I need to blow up the weights of the edges, I get a very good approximation of the complete graph. So expanders give us the best approximations we know of the complete graph. And that's a good place to start. We need to know that you can approximate the complete graph before you start worrying about whether or not you can approximate any others. The best approximations of the complete graph are given by what are called the Ramanujan graphs, or Ramanujan expanders. These were, I guess, discovered independently by Margulis and Lubatsky, Phillips, and Sarnak somewhere around, I think, 1988. And all of their eigenvalues lie in a very tight range, between d plus or minus 2 root d minus 1, and that is known to be optimal. If you have any deregular graph, or family of deregular graphs as n grows large, there will be some eigenvalues that approach those bounds. So these graphs are really optimal. The Ramanujan graphs, also being so optimal, have had a lot of applications in theoretical computer science that other expanders don't. Optimality is often a really useful thing.
And lambda value stands for all the eigenvalues but 0.
Yes, thank you for asking. Yes, lambda for me is all the eigenvalues but 0, lying in this very tight range. And you notice these two terms converge to each other as d grows large. Well, relatively anyway. So our natural question is, can we approximate every graph as well as the Ramanujan expanders approximate the complete graph? The answer I will tell you today is, I don't know, but we can get within a factor of 2. Meaning, for every graph, we can approximate it at least this well using only twice as many edges as the Ramanujan graph would approximate the complete graph. And also, the proof is easy and elementary. If I was speaking for an hour and 15 minutes, I could probably do almost all of it, but we'll see what happens. Depends on how much energy we all have. Maybe I'll just post the slides so you can check the details later if you want. Okay, so let me go back to telling you why before we get into proofs. Again, I told you my main motivation here came from numerical linear algebra. Teng and I were looking for nearly linear time algorithms for solving systems of linear equations in Laplacian matrices. When I say nearly linear, I mean we wanted algorithms that would run in time proportional to the number of non-zero entries in the matrix. And we found those, and one of the key ingredients in these algorithms were algorithms for sparsifying graphs. And why were we doing that? Well, Laplacian matrices are just everywhere. They show up if you're looking in, well, classically solving elliptic partial differential equations. More modern applications are in optimization, solving problems like maximum flow, and they're all over machine learning and semi-supervised learning, and they just come up a lot. So we were very motivated to try to solve these systems of linear equations. But there are other uses, of course, as well. Often people have massive graphs, and they want to approximate them by something that's easier to store and faster to compute with. And well, this is a fairly good approximation. It preserves eigenvectors and eigenvalues and electrical properties. Another reason we wanted to do it is, of course, to generalize expanders. Expanders have been so useful, we thought these may be useful as well. And finally, this last motivation won't make sense. I'll explain it to you in a moment. It gets us what we call certifiable cut sparsifiers. So we were inspired by another notion I'll explain in a moment called a cut sparsifier. It is a weaker definition, and there were algorithms for producing them. The only drawback is they're randomized algorithms, and you don't know if they work. So the frustrating thing is you run the algorithm, it works with decent probability, but there's no way of checking if your answer is right. This turns out to be a stronger notion, and you can check if you have it, because you can actually compute eigenvalues, where solving some of the cut problems are indeed hard. So I'll tell you just what cut sparsifiers were. It'll help you believe that spectral sparsifiers should exist. These were introduced by Bengtser and Karger in '96. They showed that for every graph G, there's a graph H, with like n log n over epsilon squared edges. The size of every cuts are about the same. So you could say this is for every vector x that lives in 0, 1 to the n, so every characteristic vector of a set, the value of the quadratic forms on those characteristic vectors of sets were approximately the same. Or you can understand this as saying for every single set of vertices, the sum of the weights of the edges leaving that set in G and in H are within 1 plus or minus epsilon of another. So this is very useful if you want to solve cut problems in graphs. It says you don't have to work with a dense graph. You can quickly turn it into a sparse graph and then solve the cut problems there. And it was because of this theorem that we thought the spectral sparsifiers might exist. The main difference is we need not all x and 0, 1 to the n, we need all x and Rn. But it's a related condition.
Is their proof constructive?
It's randomized. They find them. But yes, it's an algorithm. And it actually runs in nearly linear time. So it's handy. I can tell you what they do. We're going to do something similar at one point in this talk. Is basically they sample every edge with some probability. And they just have to figure out what those probabilities should be. And when they include an edge, they blow it up with probability. They multiply it by the reciprocal of the probability they sampled it with. So in some sense, you get a matrix which in expectation is your original matrix. And then you need to get some deviations. Okay, so let me do an example that is going to point out some of the obstacles we'll face in our construction. This is what I call the dumbbell graph. So let's start out with a complete graph on n vertices, another complete graph on n vertices, and just one edge between them. All of weight 1. Here's the right approximation for this. The right approximation for this is a deregular Ramanujan graph times n over d on either side. And then just one edge of weight 1 in between. The reason I like to point out this example is this tells you, even if you have a graph where all the edges had weight 1 initially, when you approximate it, your approximation might need to have wildly different weights on edges if you want it to be sparse. This edge in the middle of weight 1 is the same weight as initially, and you greatly downsample the edges here, but you blow up their weights correspondingly. Now, you already know enough to prove that this is a good sparsifier. Let me show you the proof. It is completely trivial given this notation of less than or equal to that I gave you on graphs. So what you do is you divide your graph up into 3 parts. The left part I'll call G1 or H1, the middle part G2, H2, the right-hand side part G3 and H3. Okay, you can apply this notion of less than or equal to separately. Your graph G you can write as say G1 plus G2 plus G3. Or at least you can do that for the Laplacian matrices. That's how we'll define plus. And you know, because of the theorem I told you earlier, that Ramanujan graphs approximate the complete graph, that G1 is less than or equal to 1 plus epsilon times H1. So you have a less than or equal to 1 plus epsilon on the left, you have a quality in the middle, and another less than or equal to 1 plus epsilon. You just add those 3 inequalities together and you get this bound. This less than or equal to is a very powerful notation for graphs. It simplifies a lot of proofs in the area. Actually, I at one point taught a course in spectral graph theory where I tried to prove pretty much all of the classical theorems about expander graphs just using the fact that they approximate the complete graph and using this notation. Okay, let me tell you now what our main theorems are going to be. Well, maybe I'll even say something tighter in the end. First, I will show you that for every graph G, there's a graph H, where H is an epsilon approximation of G. And the number of edges in H is at most 4 times the number of vertices in G divided by epsilon squared. The epsilon squared is necessary. Maybe someone will one day make the 4 into a 2. But we won't get any better than that. And F is a subset of E. So the edges in our subgraph that's approximating are actually a subset of the edges in the original graph. This I'll prove to you exists. There is a polynomial time algorithm for constructing it. It is not yet efficient. If you want efficient algorithms, we have a random sampling algorithm, which I will explain just briefly, which though costs us a logarithmic factor on the number of edges. The number of edges is like n log n over epsilon squared. It'd be very interesting to come up with something that's really fast, that gets bounds, like from this first theorem. But we don't have that. So actually, I'm going to prove something. Oh, yes.
So if I add all the computation together, the amount of computation that I do to get this, would it overall how much will I be better off than doing the computation on the full graph, as opposed to...
For these sparsifiers up top, you'll be worse off. For these, for most problems, like say a maximum flow computation, you'll be better off doing the sparsifier. This we can compute now in time, I guess it's n log squared n. No, wait, let me take that back. It might be n log cubed n, I gotta think, to get it right. There have been many, many recent improvements in all of these algorithms. It's very active, so I gotta check. But we can get this down pretty fast. I'll tell you the idea behind it in a moment. But first, I'm also going to prove something a little more concrete. Rather than with epsilons, I'm going to try to do most of the math, and this is what I could hope to teach in one lecture, getting h being a 3 approximation of g and only using at most 6n edges. So I'll often throw in numbers like 3 and 6, and there'll be a 13 that comes in for odd reasons. Okay, so let me turn this into a problem about approximating matrices, which is what it's really about. It took us a little while to figure that out. So really what we need to show is that for every vector x, we need to show that the ratio of the quadratic form in h, the quadratic form in g, well, for the numbers I put on the previous slides, I want to get the ratio between 1 and 13. Now that looks like a messy thing to do, but you can simplify it. Just do a change of variables. Set x to be the square root of the pseudo-inverse of the Laplacian of g. Please excuse my -1/2, that should be a pseudo-inverse, times the vector z. You do that substitution, and you get a nicer quadratic form. You get z transpose z in the bottom, and you just need to get all the eigenvalues of this matrix, where you want the value of the quadratic form always to be between 1 and 13. That means you just need all the non-zero eigenvalues of this matrix here to be between 1 and 13. Okay, so as I said, it suffices to do this with all the eigenvalues of this matrix between 1 and 13. Let me look at this matrix in a little bit more detail. I'm going to write the Laplacian of H. H is the matrix I'm going to construct in a special way. It's a sum of elementary matrices, one for each edge. Remember, my Laplacian of G was written as a sum of elementary matrices. Each of those is an outer product of one vector with itself. The vector, I think I wrote it before, it's BUV, but now I'm going to write it depending on the edge, so it's BE. And then there's a scaling factor. You've got to figure out what weight am I going to take each edge. I'll write it here as SE. I'm going to write LH that way. So now I've rewritten the problem a little bit. I want to write a sum of this form, where I've got a sum over edges of some scaling factor times the elementary matrices with LG to the -1/2 on either side. I want all the eigenvalues between 1 and 13, and I want almost all of these scaling factors to be 0, as you summed over the edges. Or alternatively, I really only want at most 6n terms in the sum. Okay, this is just restating that. I'm going to then rewrite this again, if you'll excuse me, that BE times LG to the -1/2 term, let me call that VE. It compresses things. I really want to write this sum as a sum of VE transpose with a scaling factor, and then I want all the eigenvalues to be between 1 and 13. Okay, there is something here that is going to help us solve this problem. There's a reason this transformation was useful. If I look at the sum of all the VE transpose terms, it turns out to be, if you carry it through, the identity. So at least, I was assuming an unweighted graph G here. If I didn't put in weights terms, it would take up too much room on the slide. Okay, that's a little bit messy to see, but maybe you should think that the sum of all the VE transpose terms was the Laplacian. So you just take the sum of all these vectors. So I've got, here's the picture. I have a set of vectors. Think of them as m vectors living in Rn. M is the number of vectors. I've got one vector for each edge. Their sum is the identity, which means if you take a look at those vectors and look at their moment ellipse, it's the sphere. Sometimes people call this a decomposition of the identity. So I have a bunch of vectors. The sum of whose outer products is the identity. And now I want to take a sum of a subset of them, rescale some of them, and get something whose moment ellipse is close to being the sphere. So, I forgot, I had a slide here explaining what I mean by moment ellipse. It just means for any vector, this should have said unit vector u. For any unit vector u, the sum of the squares of the inner products of u with all my vectors is always 1. So in any direction you take a look at quadratic things, this looks like the sphere. Our problem is now, as I say, taking a subsample of these vectors will get us a subgraph. We'll take a subsample of them and we will rescale them, multiplying some by FDs. And we want that ellipse, when we take the moment ellipse of this piece, it's not too far from the unit sphere. In our example, we need for every unit vector u, when you look at the sums of the squares of the inner products, it's between 1 and 13, and that will suffice. So we've completely turned our problem about graphs into a problem about matrices. Okay, let me state the main theorem again. If you tuned out graphs and you prefer matrices or operators, you can come back now. This is all we're going to be dealing with for the rest of the talk. So here's the fundamental statement. You give me a bunch of vectors, so some of their outer products is the identity in n dimensions. We'll then show that there are scalars, so that when you take the eigenvalues of a sum of these scalars times the outer products, all the eigenvalues are between 1 and 13. And we're only actually using at most 6n of the vectors. So we'll use few of the terms in the outer product. You can tighten this up. So if we optimize the proof, and I say I want at most dn terms to be non-zero, all of the eigenvalues I get will lie between 1 and d plus 1 plus 2 root d, and, divided by d plus 1 minus 2 root d's. And of course, if d grows large, this converges to 1. So it's really a statement about vectors we're going to prove. And there's very interesting questions about what sorts of things are true about arbitrary vectors, and what things are only true about the vector spaces we get from graphs. This talk today is everything I'm going to do is completely true about all vector spaces. There are a few things that are special about the vector spaces from graphs, but I have not figured out how to exploit them yet, at least in this work. Okay, maybe it's a good time for me to ask if there are any questions on this theorem, because this is what I'm going to spend a lot of time on. And what I mean.
There's nothing about the sum of the, just like the mean value?
Yeah, we don't. That's a very good question. So there are some applications for which you also want to control the sum of these terms times the scale. Assuming that the sum of the vectors initially was 0, there's a paper by Roman Verschijnen about, what do they call this? Lohner-John ellipsoids or something like that. And so Nikhil Srivastava has a result that extends that, it sort of shaves a log factor off of Roman Verschijnen's results on that. And he can approximately control the mean, but not as well as we like. So it's probably possible to control the mean better than we're doing right now. And it would have applications, but we don't have it quite right yet.
If you allow a few smaller eigenvalues, can you do better? In other words, if you allow some exceptions.
Oh, if I allow some exceptions, that's an interesting question. Not much better. You'd have to get to about a constant factor of them at exceptions, I think, before you could do much better. That's my guess. I mean, I could be wrong, but I don't see how I would do much better.
Yes. They exist, you really give us a recipe.
Oh yeah, I'm going to give you a recipe. I'm going to give you a concrete algorithm. So what I'm going to do is, first I'll tell you how we came up with the algorithm, and then I'll tell you the algorithm. So also, let me just tell you that, just a brief word about the random sampling approach, which is really efficient. Though this involves more vectors. This will give us n log n over epsilon squared vectors. It's very simple using a theorem of Mark-Rudelson's on concentrations of sums of random matrices. Basically what happens is to get that, you just need to choose each vector with probability proportional to the square of its norm. And if you choose it, you then multiply its weight by the reciprocal of the probability with which you chose it. And Rudelson proves you keep choosing them, and that works. In graphs, this is a really nice thing to do, because this probability is exactly the effective resistance between the endpoints of the edge of that vertex times its weight. So it turns out to have a very clean interpretation graph theoretically. It's unfortunately not something I'm not going to spend time on that result in this talk, but I wanted to mention it because it's very clean, and it's part of the fact that you get effective resistances in here is part of why we can compute all of these effective resistances very quickly, and then figure out exactly what probability we want to sample the edges with. But using random matrix theory results, I should say, the key point here is you can get down to n log n. Using random sampling techniques, you cannot get below n log n. There's a coupon collection problem that goes on. I mean, actually, random sampling fails if my vectors correspond to just elementary unit vectors. If you have only, say, 4 times n of them or something, you'll miss some directions when you do random sampling. Okay, so let me get back to the existence theorem, but I'll do it with 13 and 6 for my parameters here. Okay, so what we want to take a look at is what happens to the spectrum of a matrix when we add a vector to our collection. So what happens when we add a new outer product? So in this picture, you should imagine that is the real line, and the blue dots are the non-zero eigenvalues of the Laplacian. So when I add a new outer product, the first thing you probably know is we get what's called interlacing of eigenvalues. These circles here that are empty represent where the old eigenvalues were, and each new eigenvalue lies between a pair of the old eigenvalues, and they can only move over one. So that's a classic result that it's easy to prove interlacing. You can also make this quantitative, which I want to do. It'll help our intuition a lot. So if you actually write the characteristic polynomial of a piece of A, of the matrix A, that's the determinant of course, x times the identity minus A, we can understand how that characteristic polynomial changes when we do what's called a rank 1 update. This is a thing people study all the time in numerical linear algebra. It turns out to be very useful. We can understand exactly what the new polynomial is. It's the old polynomial times this term here. I know this is a little bit messy. I'm going to give you a physical interpretation of this term rather than try to go through the formula. So here's my physical interpretation. By the way, I should have said it, my new polynomials, it's actually the zeros of this thing. But. So here's my physical interpretation. Let me tilt this line. I imagine my eigenvalues lying on a slope. And I take my old eigenvalues, and I'm going to put a little barrier, one for each of the eigenvalues. Imagine it's a little pole that's charged. My eigenvalues are little balls resting against these barriers. Okay, so what happens? Here's my interpretation. When I add a new vector, it is going to put a charge on some of these barriers. We're going to imagine that the charges repel the eigenvalues, but the eigenvalues are also weighed down by gravity. So how much do I charge a barrier? And when I'm adding a new vector v, if ui is the eigenvector corresponding to eigenvalue ui, I charge the barrier proportional to the inner product squared. Every barrier repels every eigenvalue, above and below. So an eigenvalue can, if I charge this barrier, this eigenvalue can't get past it. Also in the limit, no eigenvalue can get past it. So that's the way I understand this formula. So here was my picture to show you that every eigenvalue repels every barrier repels every eigenvalue. So if you think about it this way, when you charge the barriers, the eigenvalues will move up, but they move up depending on how much you hit them, but they can't move too far.
So does the next barrier repel
yes, the next barrier repels.
As opposed to gravity.
Gravity pulls it down, but you need the next barrier to repel, because you can always stick enough charge on it to overcome gravity. But you can't stick enough charge to overcome the barrier because it's an inverse law. And this is this one here in the formula I had before, it's gravity, and these are your inverse repulsion laws. And all of them are repelling each other. Now, I want to show you some examples, because there's one thing here that's going to be completely counterintuitive. That is, you're probably asking yourself, what the heck happens if I just add some multiple of u1 to my matrix? Because you know that you can get the first eigenvalue to shoot up, any eigenvalue to shoot up as much as you want by adding a multiple of its eigenvector. So let's take a look at that example. So let's say that I put all of my weight on u1. I add a vector in direction corresponding to my smallest eigenvalue. Okay, there are two ways to analyze this. One is that you ignore all the other eigenvalues. They're completely irrelevant now. This is simultaneously diagonalizable. And you just see that this charge is going to push up that eigenvalue until it balances the force of gravity, forcing it down. Okay, now you're wondering, how do I relate this to interlacing? Okay, this is the wrong picture to have in your mind. Really what's happening is this eigenvalue that was here got pushed up until it hit this barrier. And the next one got pushed up until it hit the next barrier, and the next one pushed on it. That's the right picture to have in your head for what happens with the rank 1 updates. The reason it can't push past this barrier, well, even though it has 0 charge, or we're going to have 0 over 0, makes a problem. So you don't get to push them past the barriers.
How do you interpret splitting and degeneracy?
What do you mean?
Like if you have multiple eigenvectors.
Oh,
in the same
very good question. Yes, okay, so imagine you have many eigenvalues at the same place. Okay, it's a little bit tricky, but I've got many, many little barriers. You should put them in exactly the same place, and only one eigenvalue can get knocked free at a time. So rank 1 update. So here's sort of my picture. If I have these barriers, you should really think of them as all lying right on top of each other. When you make if you have multiple eigenvalues, one eigenvalue can get knocked free at a time. And that's it. And then if you add another rank 1 vector, another one can get knocked free. But yeah, so that requires putting these barriers infinitely close together, but you can do that. Okay, so this is my picture for what's going on, which was, I don't know if this is going to help you with the proof, but this is how we came up with the proof. So I'm going to try to tell you how we came up with it. Another good example is what if I put equal weight on, say, 2 of these eigenvalues. The first 2, what will happen? The top one, it'll shoot up. It gets, you can ignore the other eigenvalues, and this one now gets some real repulsion from both of these, so it doesn't get all the way to here. Actually, it should have gone a little bit less than halfway because of gravity. I don't know if I drew that. But this is the picture I have in mind. Now, the most important example for us is what happens when I put all equal weight on all of the eigenvalues. If I put equal weight in the direction of all of the eigenvectors, all the eigenvalues march up just a little bit. And in an amount we can understand. So now let me actually show you, we can understand cleanly what happens to the characteristic polynomial when you do that. So again, here is my formula for the update of the characteristic polynomial. Imagine what happens when I add a vector v whose inner product with all of the ui's is the same. Let's say its square of the inner product is 1. My new characteristic polynomial becomes this, which is actually just equal to the old characteristic polynomial minus its derivative. So if you were so lucky as to have a vector that you could add in that had equal inner product with each of the present eigenvectors, what it would do is it change your characteristic polynomial by subtracting its derivative. It's a very handy formula. So this was our first idea for a proof. It will not work, but let me tell it to you anyway, because it motivates our later argument and the bounds that we get. So here's the next fact. In expectation, a random vector acts like a balanced vector. Meaning, remember, our vectors were a decomposition of the identity. So while we don't actually have a balanced vector, we do know that for every single eigenvector, its expected squared inner product with a vector from our set is actually equal to, oh, well, the sum of them is 1. The square is 1 over n. And so the expectation is 1 over n. So here's the thing. We don't actually have access to vectors that will have the same inner product with each of our eigenvectors. But in expectation, the vectors in our set do have a uniform inner product with each eigenvector. Because they have the same inner product. The sum of the squares of the inner products is just constant. Because we had a decomposition of the identity. Okay, so here was our ideal proof. What if we could add this expected vector in every single time step? What if we had access to one of these? So our ideal proof is you start out with no vectors in your set and a characteristic polynomial of x to the n. In your next step, imagine we add a balanced vector, so it points into the same inner product with everything. What will our new characteristic polynomial will be? It will be x to the n minus 1 over n times the derivative of that. And we pretend we could add a balanced vector again. Say we know we can in expectation. Our new characteristic polynomial is, well, just you apply this operator squared to the original characteristic polynomial. And you keep doing this. And if you keep doing this over time, the eigenvalues march forward in a very nice way. And then you ask yourself the question, when you're done, is the ratio of the largest eigenvalue to the smallest at most 13? Well, it's better than that. Actually, if you keep going, the ratio of them tends to 1. And you can prove this because this operator exactly gives you a classical family of orthogonal polynomials called the associated Laguerre polynomials. And we understand the asymptotics of the roots of these exactly. And they exactly turn out to be this d plus 1 plus 2 root d over d minus 1, d plus 1 minus 2 root d bound I showed you earlier. So the bound I'm going to prove to you is exactly what you would well, the bound we eventually prove. I guess I won't do it in this lecture. is exactly the ratio of the roots that you would get from the associated Laguerre polynomials, and that's exactly what this expected argument gives us. But of course, I don't have access at every step to vectors that do this expected thing. I only have actual vectors. So the question is, how does it differ? Well, your intuition is things should be okay. What I want to do is I want to add in vectors that sort of have larger inner product with the small eigenvalues and smaller inner product with the high eigenvalues at each time, and try to balance things out. So you ask yourself, can you? Well, we tried an induction first. I'll tell you the induction that doesn't work, and then I'll tell you the one that does. I said, okay, let's try to keep all of our eigenvalues between two barriers. I'll put a lower bound to begin at -n and an upper bound at n. And initially all the eigenvalues start at 0. So our question was, can I keep moving these barriers forwards and adding a new vector in each time? So what happens? At every time step I add a new vector, and then I'll shift the barriers a little bit. The way I shift the barriers is the upper one, to get these bounds I will advance by 2. And the lower barrier I'll advance by 1/3. So I'm more conservative in the lower barrier, more aggressive in the upper barrier, but I should be, because when I add a new vector, I push the eigenvalues forward this way. So we'd like to try that proof, and if you keep going, let's see how I have this going here. If you do this for 6n steps, eventually my lower barrier would be at n, and my upper barrier would be at 13n, and hopefully all of the eigenvalues lie between the two barriers. That was our ideal argument. There's just two problems with it. Sorry, so this gets to the approximation. One, you need to show that there's always some vector you can add. And how are you going to do that? I got to show there's some some vector in my collection I can always add. Well, I need a good inductive hypothesis. And the fact that my eigenvalues lie between these two barriers is not strong enough for the inductive hypothesis. This is actually related to the question I got from the back. If I have, let's say, my lower barrier, I'll draw it here. Let's say I have 2 eigenvalues right there. Well, when I make a rank 1 update, one of them can move up, but the other one's going to be stuck there. So there's no way I can move the barrier. So we needed a stronger induction hypothesis. Here's the one we came up with. We're going to make this qualitative statement that the eigenvalues are below the barrier quantitative. We want to measure how far below the barrier they are. And we do that by introducing what we call this upper barrier potential function. If our barrier is at u, we take the sum of 1 over u minus the eigenvalues. You can also write this as the trace of u times the identity minus a, or the inverse of that. This is our upper barrier potential function. So when I know, and we're always going to keep this for purpose of induction, that this function is always less than or equal to 1. So if this upper barrier potential is less than 1, then you know a number of things. 1, the largest eigenvalue is always not just less than u, but well less than u. Well, less than u minus 1. But you know more than that. For example, you know that there can't be 2 eigenvalues within 2 of the upper barrier. Or there can't be 3 eigenvalues within 3 of the upper barrier, and so on. As long as I know that this thing is less than or equal to 1. Actually, many people have asked me, how did we come up with this function? If you actually read the paper, once you have this function, the proof is almost immediate. It's just sort of elementary arithmetic from here on. The answer is, we didn't have any magical insight to come up with this potential function. We tried a zillion potential functions. And with many, many, many days and weeks of painful analysis, until we found one that worked. So I don't want anyone to think that someone just magically guesses the right potential function. That's not the way things happen usually.
And what guided you to look for one in the first place?
That may have been magic. Actually that has been that I have had a belief for maybe 20 years that there are many things that can be proved by the choice of the right potential function. And I have many examples. So, if you ever look at interior point methods in linear programming, it's a wonderful example. But it's a very common sort of proof technique in computer science. And when you get the right potential function, everything just works. If you don't get the right potential function, usually one thing works, but then 2 other things break. Okay, we also make a lower barrier function. It's the same thing. The eigenvalues we want to be above the barrier, so we take the sum of the reciprocals of the eigenvalues minus the barrier. And for induction, we always want this barrier function to be less than or equal to 1. And now here's the way the argument goes. In the beginning, we put our barriers at n and minus n. You can now, and all the initial eigenvalues at 0, so you can evaluate the values of the barrier functions. It's really this n times the sum of 1 over n times. So the barriers start out at 1, the barrier functions. And then we need to do an induction. And it's very easy to do this induction. So we can do induction with this. I guess I don't have time to go into the proof. I'll show you 1 or 2 details. But when you carry it out in the end, we prove a lemma that you can always choose a vector so that the potential functions stay less than or equal to 1. I advance the upper barrier by 2 and the lower barrier by 1/3. Here's one thing. I'm not just choosing a vector. I'm choosing a vector times some scale parameter. That scaling is actually important, as I'll explain why in a moment. Without that, our proof doesn't work. Without that, our proof would be much better, but it's there for now. Okay, so when you're done, this will get us the bound of all eigenvalues lying between n and 13n. Okay, I'm not going to do details, so let me tell you 2 parts of the analysis. What we do is we actually, to address the question of when can you add a vector times its transpose and S times that vector, it's a fairly elementary computation based on the trace formula for these potential functions. You use the Sherman-Morrison formula for how traces behave under rank 1 updates. So there's standard sort of things for how inverses behave. We find out that we can add S times a vector and move the barrier from u to u plus 2 and have it be less, the potential function be less than or equal to what it was before. If and only if, well, there's some quadratic form, I'll call it UA, that needs to be less than or equal to 1 for this vector. So I need that S times my vector transpose times UA is less than or equal to 1. Same thing for the lower barrier, but I need this quadratic form to be greater than or equal to 1. And sort of the reason is the upper eigenvalues you don't want to push too much on. Actually, the upper potential function would be happiest if you add nothing. And the lower potential function would be happiest if you add a lot. It pushes the eigenvalues far from the boundary. So we need to prove 2 bounds like this. Now, what we happen to know, we can show pretty easily, is that in expectation over the choice of vectors in our sets, the expected value of the upper quadratic function is less than or equal to the expectation of the lower quadratic function. So we prove that. And this is an easy calculation, because it actually just rests on the trace of those matrices UA and LA. Okay, once we know that in expectations one is less than or equal to another, that tells us that there exists an edge E for which one quadratic form actually is less than or equal to another. That's how you deal with 2 expectations. And then, once you have that, you just got to multiply by the appropriate S that puts one of these between each other. That's where our scale factors come from. And I told you in general we need some scale factors for general graphs. So we knew we were going to have something like that anyway. Though there's some situations in which we'd like to get rid of it. Okay, so that is the heart of the proof. As I said, we get this twice Ramanujan bound, I called it. If we optimize the parameters, sorry that makes the paper a little messier, you get dn steps, and you get this optimal ratio of the largest eigenvalue to the smallest eigenvalue, which is again the ratio of the largest root of the associated Laguerre polynomial to the smallest root of that polynomial, asymptotically. So we get the right bounds. The reason this is twice Ramanujan, actually, if anyone is good enough to remember the formula I had for the ratio of the eigenvalues to the Ramanujan graphs, this expression is actually slightly lower than that. So you might think I'm getting something better than Ramanujan graphs. We're not. The reason is we have twice as many edges. I have d times n edges, and a d-regular Ramanujan graph actually has d times n divided by 2 edges. So we're at most twice as many edges as you would have for the Ramanujan graph. Okay, I want to quickly mention, I guess I'll do it very quickly since I see I'm out of time, just 2 related things. One, this potential function argument is very useful. So it gets us a very simple proof, this Morgan-Safiri restricted invertibility theorem. Roughly what that theorem says, let me not put up this formulation, let me put up this one. Whenever you give me a matrix in which all the columns have norm 1, you can pick some appropriately sized subset of those columns so that the operator just restricted to those columns is, well, they call it well invertible, has a large, smallest singular value. And There have been various forms of this with some sort of constant c in there. It started out at about 10 to the minus 72. It's improved over time, but if you just use the proof technique I showed you, you actually get the constant c being 1, which is optimal. And you get a very, very clean proof. It's just about 2 pages. Well, maybe another page of introduction. But, so you get a very clean proof of this using these potential function arguments. There's also something very nice. We only care about one eigenvalue. When we only care about, let's say, one eigenvalue, the lowest or smallest, the potential function arguments don't have these scale terms. We just take vectors. And that is very provocative. Because there's another problem that looks a lot like ours, which doesn't have these scale terms. There's a famous conjecture of Caddison and Singer, which has been shown equivalent to a zillion other conjectures, famously the paving conjecture, and a recent one by Nick Weaver he called conjecture KS2 prime, that looks a lot like ours. Let me just tell you briefly what it is. Well, actually, I'm going to give you a strengthening of it. It would say that there's a constant alpha. So whenever I have m vectors in n dimensions, they should be a decomposition of the identity, and all my vectors should have the same norm. Let's say that norm will be less than or equal to alpha. So alpha just constrains the ratio of n to n. It suggests that there's a subset of half of them, so that when I take a look at the sum of their outer products, we won't expect all the eigenvalues to average to a half, but you just want all of them to be between a fourth and 3/4. This is very close to what I've shown you so far. So let me show you how close it is. If you take a look at Rudelson's random sampling, it would get you a statement like this, except it would need alpha not to be a constant. Alpha would be like a constant divided by log n. But it would exactly do this. Our statement does this for a constant, but we don't get a sum of the vectors. We have a sum of the vectors with some scaling factor. Here's the next annoying thing. If all the vectors have the same norm, we don't know why that scaling factor has to be there. We know no reason why that scaling factor has to be there. So it feels like this is getting close to the Caddison-Singer conjecture. I don't know. I mean, we've been trying to prove it now for 2 years without success. So it's clearly not a neighbor of the Caddison-Singer conjecture, but maybe it gives you some more reason to believe it. And this would have a whole lot of implications. And I will mention just one weaker thing we don't know before I leave. This is implications for approximating the traveling salesman problem. We don't even know this same statement where one eigenvalue is just strictly greater than 0 and the other one is less than or equal to 3/4 if you don't scale it. And if you can prove that, it is, well, at least very close to what we need to get constant factor approximations for the H-symmetric traveling salesman problem, whereas the best known are like log n over log n. And let me leave just asking a few questions. Okay, even easier question than I asked you is, can you apply a similar technique like ours for the complete graph? I told you Ramanujan expanders are great approximations of the complete graph, but we can't construct them for any complete graph. They're only sporadic examples. They depend on number theory, or, well, there's a recent paper I saw using Octonius, so maybe that'll get us more. But when we have a complete graph, there's no reason to put weights in our construction, but we don't know. Can you get to the Ramanujan bound? I suspect that is using something special about graphs and the vectors we get from graphs, as opposed to just arbitrary vector spaces, but I don't know. More general, there are questions about when I take these vectors from graphs, what happens? Again, there's some special things that happen we know spectrally, but we don't know much more. This might be what explains why you get the Ramanujan bounds. One last question is, can you come up with a faster algorithm for doing what we do? Usually if you want to choose like a random expander graph or something like a Ramanujan graph, you should do something like take the union of a constant number of random Hamiltonian cycles to the graph. Can you do anything like that here? There might be a fast randomized algorithm for getting linear size sparsifiers like we do, that are not quite optimal, but we have no idea. It would be useful. And then I'll mention, I guess, I already mentioned the asymmetric traveling salesman and Caddison-Singer, so I'll stop there.
Points in the real numbers. You put in complex numbers, and then you talk about the impedance, and then you have phase factors, and all of those things. Possibly, I don't know anything about this, but could that happen? That you would get something useful from that?
Maybe the theory gets far more complicated, even if you try to put in negative numbers. I mean, I'll tell you the main intellectual obstacle for these graphs. I know what the null space is. As soon as you do that, you're going to get a null space that could be larger, and I don't know how to understand it combinatorially. So if you had a nice family of graphs like that, where you could look at it and eyeball it and figure out what the null space is, then maybe there's a prayer of getting quantifiable bounds on the eigenvalues. But if you can't eyeball it and understand what the null space is, then there's no prayer to get a grip on the eigenvalues. And I don't know a nice family where I can. If you do, send me email. We should talk, because it's an interesting question. I say even with negative numbers, before we go complex, even I don't know. So there was a question back there. Yes.
Yeah. So you mentioned that you think that there's still a factor 2 weighting in the bound in terms of typing. Do you think another potential function could get you that or not?
I don't think so. I am not sure. I mean, okay. So let me give you the arguments for and against. The argument against is we did try many potential functions. The other argument against is that I suspect I'm not sure, but you might not be able to do better for vector spaces. This factor of 2 might really depend upon graphs. And then you need an argument that's going to take special advantage of them. The argument for is that there was an interesting paper written 2 years ago by Kola, Makarichev, Saberi, and Teng, which made some uses of some modifications of these potential functions that completely surprised me. So even though I've been playing with these for 3 years now, I don't really understand them. So, the fact that we shouldn't be taken as too much of a negative. I've been wrong before. Yes.
In your theorem, is it important that the weightings not be integral, for example? I mean, if you assume the weightings are all integers, does this change your
that does not help us. So yeah,
would the eigenvalues be algebraic integers in that case?
Oh, yes. But if your weightings are all integers, then the weightings will be algebraic integers.
So the number theorists like thinking about the number theorists like thinking about algebraic integers that have all their conjugates in a given interval. So
I see. I guess I hadn't thought about that. I mean, for me, these eigenvalues look so numbers. Dense to me wherever they are that I wasn't sure I could do anything with that.
Do you think your notion extends to directed graphs?
So that is a very difficult question in a number of ways. The problem with directed graphs is it's not clear what's the right Laplacian to define. If you define it, it's not clear it's diagonalizable. Fan Sheng, I know you're working with, has some notions that are symmetric and get you diagonalizable matrices, but I think they're cheats. I think it's missing the heart of the matter. The main problem is, in this problem, there are many notions of sparsification that are all equivalent. And when you go to directed graphs, just the same way when you go to asymmetric matrices, the notions split. And some notions of sparsification you can prove are impossible, and some others still seem reasonable. We haven't ruled them all out yet, so we don't know. But yeah, you need different notions. For example, like there's this physical metaphor of resistor networks. You can put diodes in it, and then take a look at an electrical network. But that gets you completely different things than if you start building asymmetric matrices. You're looking at the values of linear programs and quadratic programs instead of looking at eigenvalues.
But going back to this question, if you put capacitors and inductors, would that buy you anything?
A nightmare, I think. I mean, I'm just telling you, I can't handle diodes and resistors yet. I mean, I said simple diodes and resistors. I don't understand this theory for. If I understand that, then I'm willing to move on to capacitors and inductors. But until then, I'm going to win.
Any other questions? Okay, I'll just mention that those people who haven't signed up for dinner are interested. There's just a couple of spots left, and if you are still interested, you should speak with Andrei Shedrov immediately after the talk to find out if there are.
Andrei, when would you like us to meet at your office?
No, we're meeting here.
Meeting here?
Not meeting.
Okay, so meeting here in about 15 minutes?
No, we're going now.
What?
We're going now.
That's what you think.
Okay, and I'd like to